I want you to picture our sun. But forget about the warm, golden sphere we see in the sky today. I want you to fast forward billions of years into the future. By this point, its outer layers have been completely, violently stripped away, just blown out into deep space. And what's left? Just this tiny, unimaginably dense, glowing point of light sitting in the dark. It isn't generating any new energy anymore. It's really just radiating its final, trapped heat. This is what we call a white dwarf. It is, quite literally, the last lingering breath of a star.
Now, this beautifully haunting, glowing cloud is known as a planetary nebula, and it's exactly what remains after a star like our Sun finally exhausts its nuclear fuel. All that outer gas gets cast off into the cosmos, and it leaves behind that naked core, the white dwarf itself. And that core is just going to sit there, glowing with residual heat for literally billions of years to come.
Part 1. The Life of a Star. Okay, to really appreciate a star's dramatic end, we have to first understand its stable life. Think about our sun right now, which has been burning away steadily for about 4.6 billion years. Inside every active star, there is this epic, ongoing battle. It's a massive cosmic tug-of-war. On one side, you've got the crushing force of gravity constantly trying to collapse the star inward under its own immense weight. But on the other side, you have nuclear fusion, the core converting hydrogen into helium, and that creates a tremendous outward pressure of hot gas and radiation. So as long as the star has hydrogen to burn, this delicate, perfect equilibrium holds up.
Part 2. When the fuel runs out.
But here's the catch. That hydrogen supply isn't infinite. And when it starts running out, we hit a dramatic turning point. Let's walk through this timeline of absolute chaos. First, the hydrogen in the core depletes. Without that outward pressure from fusion, gravity briefly wins the tug-of-war. The core shrinks, and as it gets crushed, it heats up tremendously. This intense new heat actually sparks hydrogen fusion in a shell just outside the core. And that sudden massive burst of energy? It causes the star's outer layers to wildly expand, inflating the whole thing to absolutely massive proportions.
Part 3. The red giant phase and shedding.
As the star transitions into this massive red giant phase, it swells to hundreds of times its original size. I mean, it's going to grow so large it'll completely swallow up inner planets like Mercury and Venus. And honestly, long before it reaches its maximum size, the intense heat will have made life on Earth completely impossible. Deep inside, the star becomes incredibly unstable. It starts burning heavier elements in layers, kind of like an onion. First helium, then carbon, then oxygen. The whole star begins to violently pulsate, and eventually, the outer layers get pushed so far from the core that gravity can barely hold on to them anymore.
Ultimately, the star just completely loses its grip. Those outer layers simply drift away into space, creating that incredible planetary nebula we talked about earlier. It's like a cosmic ghost. This spectacular gas cloud dissipates over thousands of years, seeding the universe with all those heavy elements the star forged during its lifetime. And right in the center, only that scorching hot, naked core remains.
Part 4. Anatomy of a White Dwarf.
So let's dive into the core itself and look at the mind-bending physics of the white dwarf that gets left behind. Look, this isn't just a normal piece of hot rock. It's an object that totally defies our everyday understanding of matter. The most crucial thing to wrap your head around is its unfathomable density. Imagine taking the mass of an entire star, something that used to anchor a whole solar system, and crushing it down into a sphere no bigger than planet Earth. Because it's packed so incredibly tight, if you were to scoop up just one single teaspoon of white dwarf material, it would weigh tons right here on Earth.
Now you might be wondering, with all that mass, why doesn't it just keep collapsing into a black hole? Well, the answer lies in a bizarre quantum safety net. According to quantum mechanics, specifically the Pauli exclusion principle, electrons physically refuse to occupy the same exact state. So when gravity tries to squeeze them too tightly together, they push back with an unbelievable amount of force. We call this quantum degeneracy pressure, and it is literally the only thing keeping this dead star from collapsing in on itself completely.
Part 5. The Chandrasekhar limit.
But, as you might guess, quantum mechanics does have its limits. There is an absolute physical threshold to this safety net. The crucial point here is that a white dwarf can only hold off gravity, up to roughly 1.4 times the mass of our Sun. That is the breaking point. If a white dwarf somehow gets heavier than 1.4 solar masses, that electron degeneracy pressure fails, and the equilibrium completely shatters.
Which brings up a really fascinating question. How would a dead star gain mass in the first place? Well, imagine a white dwarf in a binary system, locked in a tight orbit with a normal living companion star.
Its gravity is so intense, it can actually siphon off gas from its neighbor. It just gorges itself on this stolen material until it crosses that 1.4 solar mass threshold. So what happens then?
Crossing that limit triggers a catastrophic thermonuclear explosion known as a Type 1a supernova. It completely, utterly obliterates the white dwarf. And here's why this matters to us. Because these white dwarfs always explode at that exact same mass limit, their peak brightness is incredibly consistent. Astronomers actually use them as standard candles to measure vast distances across the universe. In fact, studying these explosions is exactly what led to the discovery that the expansion of our universe is accelerating, which pointed us straight to the concept of dark energy.
Part 6. Fate of our solar system. Now, our sun doesn't have a binary companion, so it's not going to explode as a supernova. But let's bring the cosmic scale back to our own backyard and talk about what will happen to our solar system. The solitary afterlife of a star is surprisingly violent. Astronomers have actually observed a zombie white dwarf named LSPM J0207+3331. Its atmosphere is heavily polluted with heavy elements like iron, nickel, and silicon, and that tells us something terrifying. This white dwarf is actively tearing apart and consuming the rocky remains of its own planetary system. It's literally eating a shattered Earth-like planet.
And honestly, the survival rate for planets is pretty grim. Studies suggest that fewer than 3% of white dwarfs have surviving substellar companions, and almost all of those are massive gas giants. For Earth, our fate relies on a terrifyingly delicate balance. When the sun expands, will its massive tidal forces drag us in to be consumed? Or will the mass the sun loses in the process weaken its gravity just enough to push Earth out into a wider, safer orbit? Scientists are actually still running the models on that one.
Part 7. The ultimate cosmic end. Let's assume a solitary white dwarf survives, and its planetary system is completely settled or destroyed. What comes next? Well, a white dwarf is essentially a super dense core made of carbon and oxygen. Over about 10 billion years, it slowly radiates its residual heat out into the freezing vacuum of space. And as it cools, the core begins to freeze. Under that immense pressure, the carbon and oxygen actually crystallize. The dead star literally turns into a massive, solid, diamond-like sphere.
Let's walk through this final cooldown phase. It starts off as a blistering hot, glowing white dwarf. Then it crystallizes, which actually releases a tiny bit of energy and slows down its aging by a couple billion years. But eventually, after trillions of years, it will cool completely and stop emitting light entirely, becoming a cold, invisible black dwarf. Now, our universe is only 13.8 billion years old. That means it is still way too young for a single true black dwarf to even exist yet.
A white dwarf is really the ultimate cosmic memory of a star's life. It holds the history of its solar system locked inside that dense, quantum-supported core. So, will the shattered remains of Earth still be orbiting when our sun finally becomes a frozen crystalline sphere in the dark? If you want to keep exploring how the final breath of a star turns into the most fascinating science imaginable, make sure to subscribe to Universe Code. See you next time!